training your algorithms you develop. So in that case, you would then you would have many objects for use for training. You would extract the features from those objects. Those features then become the database where you would collect all that information. Then when you bring an unknown object in front of it, you still would need to extract the features. And those features then you put to the classifier, which basically takes the information and try to see where this object fits. So for example, your database might have the features of, again, like say apples and spoiled apples and or different textural characteristics of the apples. And you might say this unknown object, does it fit in the good apple or a spoiled apple, or does it fit in the this kind of texture or that kind of texture? So that's where you would do the classification. Same thing could be applied for spoiled meat or for different grains or different hard wheat or soft wheat or wheat used for making bread or pasta. So the process is very simple. So you create the database using the objects which you use for training of the system. Then unknown object basically comes in. You extract the features. Then the classifier is basically comparing that where does it, which class does it belong to. And there are tools which it would use, and we will talk about those statistical classifiers or neural networks or fuzzy logic, where it would then make a decision which group it belongs to, and gives you a really basically it is doing the probability that it belongs to this class. And there are times when it would make an error, and that error is made. That's why the classification results are typically you would have results 90% accurate, 96% accurate, or 99% accurate, which means that in other times when it's not 100%, basically making that mistake is misclassifying. So it might say wheat is misclassified as barley, for example, or barley is misclassified as oats or wheat, or vice versa. So the process you basically are trying to design is that you want to have that as less or as minimum as possible those classification errors. You also want to have as minimum as possible false positives, but you don't want to have wrong thing classified, and the results might look good, but you are misclassifying. So many of the barley got misclassified as wheat, and any wheat got misclassified as barley. Overall result might look good, but it still have a lot of errors built in them. Okay, so you need to basically characterize that. So, and once it goes to the classifier, you basically put the object in one of the class. So it's very simple from a block diagram point of view or from a concept point of view. The process itself is very straightforward and simple. So the most of the work goes into extracting the features, the initial features, and deciding what features to extract, and deciding what features are important, because you can extract many features. You can extract, when we go through the information tomorrow, you would see you could extract 200-300 features that are all important. Okay, and if you have too many features, you have made the system complex. But if they are not adding to the classification, why you need that many features? So a lot of work goes into is extracting of the features, and then the additional amount of work goes in developing the right classifier, because you have to, because that classifier is the which then takes the object and says which category it fits. So in terms of the amount of work required when you're developing a system, I would say probably 80 to 90% will go in the extracting features, and 10 to 20% would go in developing classifier. And the putting the system together and all that is a very small amount of work, because you buy the camera, you put it together, you start, and then collecting samples would fit under the extracting the features of the training set, because training set is very important for the development of the classifier. So in a typical imaging system, this is an example of a color imaging system. So in a system you would have the graduated or scaled object that you see is the stand, where you would mount the camera on it, and the camera, digital camera, along with the lens, naturally is part of the camera, and you can having a different lens, you can change the pixel size or the size of the image you would acquire. So the digital camera and the lens assembly usually moves along the stand in a typically, I would say, in a vertical direction. And what you see under that aluminum dome is where the illumination is coming from, or the light, which is typically you are lighting the object. And the object in this particular example is shown in this particular case is on that black platform on the right side of the image. There are 5 kernels sitting on that object on a black background. So that's where the objects, you are trying to put the light on the object. In this particular example, you are seeing the light is coming. There is a, I don't know if you can see, there is a circular fluorescent tube around the area, which is not that easily discussable, but that's the circular fluorescent tube is the one which is providing the light around the object. And the circular tube is right there. You can see in the vision through there, which is shown there. And this dome, which is an aluminum dome, and painted white with the metal oxide on the inside. So the fluorescent tubes is reflecting the light and reflects it back. So it gives a uniform lighting on the surface where you are putting the objects and taking the images. So the basic component of the imaging system basically is a camera, some way to support it. You need an illumination system, and you basically need and the illumination system has to guarantee a uniform lighting. And we will talk about how to ensure the uniform lighting tomorrow and how to do calibrations for the different systems. So basically, the simplest system is you ensure a consistent quality uniform light and camera to take image, and then you extract the features and then do the analysis. Okay. So in that, sorry, I should have shown. In this example, what you are seeing, so when you're taking the picture, you are taking the picture of an area. So you get a 2-dimensional image. But there are, this is referred to as area. These are referred to as area scan cameras because they are taking the picture of an area. But there is also a line scan camera. And the line scan camera, typically the picture it takes is a line at a time, and then either by moving the camera or moving the object, you create second dimension. So you take line by line, and you put the lines together, you basically get your 2-dimensional image. This is an example of a line scanning system. Again, you need the stand to hold the camera, and the number 2 is the camera including the lens, and 3 is the conveyor where the object would move, or the material would move on the conveyor, and then the image system basically is taking the acquiring the image and storing the image into the system. And both, so for a automation process, typically you would say line scan camera would be the best one, because then you can feed the object and they keep moving, and you continue to take line images, and then by putting lines together you make your 2-dimensional image, extract the information. You can also use the area scan camera for automation, but you will have to design the movement in such a way that it provides that so that there is not too much overlap on the image. Otherwise, you would be then confusing the objects. So as long as you can say that the image is taken every the gap between the next image, so the images don't overlap, you can use area scan camera also to do the pictures of the moving objects. Okay, so either one system could be used. You just design the processing part so that you don't cause overlap. And even the line scan camera, if your belt starts slipping, you can cause the problem. So you have to avoid, make sure that belt slip is taken into consideration, and you won't cause those errors. Okay. So basic component of an imaging system I had already mentioned is the camera. And there are different types of cameras you could use. The most common one is the charge-coupled device, CCD cameras. But there are also available CMOS or complementary metal oxide silicon cameras. And these are how they basically take the information from the image, the reflected light, and how they convert into intensity. So basically the different way of presenting that intensity. Thermal camera is when you are looking at the temperature profile of the object, and you would use thermal camera. Illumination, I had already mentioned, is very, very important, because if you have, I'm sure you've taken pictures when there is no proper lighting, you get very difficult to see image. You can figure out that there is somebody there, but you don't know who the person is, or depend on the light intensity, and you have to then adjust the lighting to be able to figure out the object. So the proper illumination is very, very important in the imaging system. And the major sources of the illumination could be fluorescent light, could be incandescent bulbs, which almost are now disappearing with time because of the energy efficiency issues. The halogen lamps, you could use LED bulbs. Now, there are issues with each of the systems. So, for example, if you are dealing with a biological objects and you use halogen and incandescent, and you are familiar with both of these, produce a lot of heat and get hot very quickly. So if your object is a biological in nature and heat could damage them, could die your samples, then you probably want to use the halogen lamps. If you want to use fluorescent lamps, the challenge with that is that they flicker quite frequently, so you would need a stabilizer to make sure that the constant voltage goes to them, and then they don't have that flickering. Otherwise, depending on your color, you have a different light intensity at that time. So you have to ensure that. LEDs, light intensity is not as strong as you would see. So by having so depending on which lighting source you want to use, any of the lighting source can work, but you need to understand the material you are dealing with and how you ensure the uniformity of that lighting. Okay. Other component is the frame grabber, which captures the digital frames and then stores and displays and transmits original compressed formats. So this is basically nowadays I think the frame grabber is basically replaced with digital cameras have built-in frame grabbers. So you get the digital images. These are very important when you are dealing with the analog signal coming from the cameras, and then you have to convert them to digitized cameras. And then you use the hardware and software. So the software is to extract those features. And a lot of time, I would say, in the past, people were writing their own software to extract the features. Nowadays, you can buy the software programs which can extract, I would say, certain simple features. You may have to still develop your own algorithm to develop some complex, unique features. But simple features you can buy nowadays, like MATLAB has built-in libraries to extract a lot of features from the objects. Okay. Any question? And you saw the picture in the previous slide. This one shows you in a physical component way that typically you basically would have a computer, you have a camera, you have illumination box. So like here, your object will go here, illumination box here, object will go here, camera, bring the information and do processing. Okay, and I had given you the steps earlier, so we need to now go into a little more detail. So the image acquisition, again, the steps being the image is captured by different types of sensors, and the different types here referring to the cameras, like there could be a camera for visual range, or an IR camera, or could be thermal camera. So any of those sensors would capture the image. Processing, we talked about that, reducing the noise, cleaning the image, enhancing the objects in the image. Image segmentation is separating the background from the object, or object from the background. Separate the object representation and description, and that's then characterizing of the object by extracting the features and do the classification. Okay. So then image processing techniques, when you start going into the image processing, you can group them into 3 areas. So image reconstruction, and this these are different terms. Sometimes people would use pre-processing, or sometimes you can say image reconstruction because you're eliminating those effects in the image. The different terminology use image restoration, that making the basically the image of reasonably significant quality, and then the enhancement again to contrast, increase the contrast between the object and the background, so that is a proper separation. Because if you don't have a proper contrast, and when you start separating, you might, so for example, like let's say there's a kernel of wheat, and then you take the picture and it has a shadow on it. So then when you're doing the separation between the background and the object, where does that shadow go? Does shadow become part of the wheat kernel, or does shadow become part of the background? Ideally, you don't want to have any shadow, but if you had that, then how you eliminate that it is not, because it's not really part of the kernel. So you need to then design the algorithm to clean that image. So those kind of things would fit under the image enhancement category. And then you do the image segmentation, and that is the now separate of the object from the background. The tools used for that is the thresholding, and the thresholding is the, sorry, an example given here. So you do the histogram of the image. So histogram basically is the, you have the, every pixel has a gray value. So you are basically plotting is the gray value, the number of pixels having a certain gray value on this axis, and this is basically your number on this side and glare on this side. So you would see in this particular example, you're seeing 2 weeks. So that means this wavelength or this gray level is occurring that many times, and this gray level here is occurring at that many times. You might, looking at that, you might say that maybe this would be the gray level value which you could use as threshold values. You can anything of that along this group, and anything below that along this group. So this could be, for example, object, and this could be background. So you could use a simple thresholding by doing that. And then I think today or tomorrow we will talk about that you can do the, this is the simple thresholding may not work because you have to be manually select, or you can do that by histogram a single threshold, but you could also do automated thresholding where you might then do the iterative process to find the best possible way of separating the object from the background. Another one on this segmentation is this particular example here. You are seeing what is referred to as ad-based segmentation. So you start from points. So again, keep in mind is, that's why I had asked Dr. Singh to get us the graph paper. Graph paper is a very good example of thinking of an image. The graph paper has those square pixels all over. So basically, that's how the image physically would look like. So in that case, so you start from 1 pixel, and then you do the assessment of that pixel. Does it belong to, and we will talk about the connectedness to the pixels. Either using 4 connectedness or 8 connectedness. So you decide this pixel, the next pixel, does it belong to the background or to the object, and you follow the contour basically. So you can do the segmentation by following the contour along that, or you can start with, again, 1 pixel, and then go to the next pixel and see does it belong to the object or is it not part of the object, and you keep growing. So if you keep going in this direction, for example, you would hit probably this point, the next pixel would not be part of the object because it would be in the background. Then you start second line, and so if you keep doing that, so you are going from inside to the outside, you eventually reach the boundary of the object and separate the background. Okay? So there are 3 ways you could do that separation. You do thresholding, simple thresholding, and say this is object, this is background. So you can go along the circumference of the object. Now in this case, if there are 5 objects in the image, you have to basically start from the top corner, top left hand corner, and go to the bottom right hand corner. Basically, so this scan all the image, all the pixels, and see where this belongs to, this pixel belongs to. So you can do either thresholding, edge-based segmentation, or region-based segmentation. Now there are areas, and I may be probably repeating from tomorrow where we have more detail, but the areas where the contour-based segmentation will be very important if you are interested in the features based on the boundary. So like perimeter, area, that kind of information. Whereas region-based segmentation is important because you may not hear what's inside here, and you can only do the analysis based on that circumference or the boundary, and you can extract features from that like perimeter, area, central, radius distances, mean radius, those kind of things. Region based would become very important if you're interested in what's inside, so not with the boundary, but what's inside. So you might look at the mean intensity of the color or the textural features. So depending on what kind of features you are interested in, you may use one technique or the other. Whereas the threshold base gives you the information which classifies the images into the pixels for the object. You could use for both the circumference, do the analysis based on the boundary of the object or the middle part of the object. So different kind of features are extracted from the boundary or from the interior part. Object representation and description we talk about is after segmentation, the resultant pixels are represented in the form suitable for the processing. Region is represented either based on external characteristics of the boundary or internal characteristics based on pixel in the region where we said color and textural features would come. External representation or the boundary representation is very selected when you're only interested, primarily interested on the shape characteristic because you're defining the shape of the object, whereas internal representation is chosen when you are interested in color and textural features. And based on the chosen representation, the region is described based on features such as length, orientation, and number of concavity in the boundaries. So when as the changes in the curvatures in the boundary, so you characterize those. And once you have done that, you do classification. So you identify the object by classifying them into finite sets of classes by comparing the measured features against the database, which comes from the trained set. And three main classifying techniques are statistical, fuzzy logic, neural network, and we will touch, I think, both. A lot more, I think, statistical and neural networks in the on third day when we are looking at the classification, or after we have done the feature second part. And then, as I mentioned, we would then look at on fourth day are the different imaging techniques. We would mainly focus on X-ray, hyperspectral and thermal imaging, and visible spectrum. X-ray, CT, and MRI are two other areas, but for the food process automation, they still are not at that stage. They are still, I would say, the research stage, which are commonly used in the medical field, but they can be used in the agri-food area more for research for understanding the microstructures of the materials and the distribution of the components in the material, but not ready for automation or the process automation. So we would just focus on the X-ray and hyperspectral and thermal imaging area. Keeping in mind, we are dealing with a nanometer from 400 to 700 nanometers. That's the range we are dealing in the visible spectrum. And then applications of the in canola, so different grain types, very high accuracy, over 99%. Classes are referring within the same grain type, different classes. So like in Canada, we have 8 wheat classes, like hard spring, hard winter, soft white, durum. So there are 8 different classes, and again for class identification, very high accuracy. On cultivars, on the other hand, are within the same class. So hard red spring wheat might have 20 different cultivars or 15 cultivars grown in the country. So identification of the cultivars accuracy was not as great, but it has a potential to identify. So example, detection of dockage components in the grain. So the different foreign material in the grain, different component like the chaff present in the grain, or weed seeds or dirt particles. So identification of those. Dockage components, foreign material. So the difference between the dockage and foreign material is that typically the dockage is something which can be removed by physical sieving, and the foreign material is what remains with the grain after that sieving. So for example, chaff particle and dust particles or dirt particle could be removed by sieving, then it would be considered dockage. And then like say barley kernel in a wheat sample remaining after a sieving, because barley is very similar, it cannot be separated by sieving, then in that case barley would be considered foreign material in wheat, as an example. So it can identify the foreign materials, fungal infection, discoloration in pulses. Yeah.
So we can determine oil content in oil seeds by imaging in visual spectrum. Is it possible?
Not in the visible spectrum.
By bioimaging
We can, yes.
Just by looking at the grains, oil seeds, sorry.
Yeah. So not using the not in the visible. So like for example, with the NIR spectrum, you could detect the oil amount of oil in the sample by taking the image in the NIR spectrum and doing the analysis. You could detect the amount of oil.
Sir, in NIR, I think I have worked with the NIR regarding where in the field they use NIR instrument where the first of all they took non-samples with the non-protein content, fat, moisture, ash content, and then they feed the sample into NIR for just calibration, let's say 30 samples.
Yeah.
And then they put unknown sample into NIR and the instrument tells the fat content, moisture, protein out of that calibration range. So is it with the similar case with oil seeds if we want to know the oil content?
Same idea. So here what you would do is that you are going to give the samples with different oil level, and it would take the NIR, but now you are not taking the NIR spectrum as the NIR spectrometer does, because it typically sends the light through and then you collect the transmitted light. Here you basically would light the sample with a NIR light source. So the sample is now, so rather than reflecting from the sample the visible spectra, it is now reflecting in NIR spectra. So your gray level or intensity level you are getting is now in the NIR range, which is not visible to the human eye. That gray level intensity distribution, or the features you would extract from the gray level intensity distribution, you then relate that to the oil content or protein content.
Similar with what they have done with the
yeah, so you still would have to do the calibration, but the calibration is done more from what you get from the image rather than what you get better range. Yeah. Okay. But this one is just the examples I'm giving from our research, what we were able to use the visible images in the visible spectrum, and what kind of things we were able to detect with a very reasonably high accuracy. So detection of fungal infection, discoloration in the pulses. Pulses are like people are very sensitive to the color of the pulses. If the color discolors, people don't buy the pulses, and then you have to guarantee the consistent quality. Detection of rice color, again for the same region, the whiteness is very important for people. Detection of the flower color, so that you are making sure that there is no ash content and not too high ash content. And assessment of the particle size distribution in wheat flour can be done by using images in the visible spectrum. Okay. For fresh produce, for example, in the visible spectrum, it can be done for detection of blemishes, disease, greening of skin, grading of potatoes, detection of bruises, insect bites, rots, surface defects in the potatoes. Automatic quality grading system developed for strawberry, raisins, mandarin, tomatoes. So these are all done in the visible spectrum. And when I say visible, it's basically using your camera, which we nowadays carry in our handheld devices. And those cameras are almost as powerful as cameras 10 years ago, when you would buy specifically for research purposes. And in the food product, color or texture evaluation of ready-to-eat meals, quality grading of various meat based on color, texture, and estimation of the fat content, and inspection of food packaging, bottles for fill levels and cap closures. And even the label identification, the label is properly identified, making sure the coding for the date is done properly. So those kind of applications all can be done in the visible spectrum. Yeah.
Demonstrate how to segment the data.
We would do that tomorrow.
Okay.
Yeah.
Capture and how to do it, and particularly how to use the network.
Yeah.
Because they should understand how to use the MATLAB.
That's why I brought the Chala. So do they have a MATLAB here? Because if I had asked that, do they have a MATLAB available?
I think it is available.
Yeah. So if it is available, then we can demonstrate that part. Yeah. And we would do some even by hand. As I said, we would extract the features by hand, and once you extract by hand, then you can start
For
appreciating.
example, one of my students, she's working on developing eggless recipe for cakes.
Yeah, yeah.
And we are always interested to know the pore size, whether it is uniform or not.
Yeah, yeah.
And we are doing by the sensory evaluation, by asking the panelist. But we don't get consistent results.
Yeah.
But the image analysis for that work would be very good.
Yeah, and it certainly would fit in this category of the previous slide, the flower particle analysis.
Yeah.
I know. Flower particle analysis, this one here. Particle size distribution.
I don't know if is it possible for particle size analyzer.
Yeah.
For example, we have a particle size analyzer that the cost of that instrument is very expensive. They are 40 lakh rupees. But if we can develop some method that by image analysis you can measure the particle size, and then we can see the correlation with the actual particle size.
Yeah.
And then if we can develop some application for the flower test.
Yeah, it's possible. To me, I think it's possible. Yeah, because it can be used for.
Because like in our country, the hardness of the wheat variety varies from 10 to 90. It's a wide range, and the quality of flour we are getting very tremendously in your particle size distribution.
Yeah, yeah. So particle size distribution can be done by the image processing.
Then it will be a very good method instead of going.
And then I think like I would go even further that I think if the proper algorithms are developed, then even people can take image using their nowadays with their digital camera or handheld device, send that to a central lab which can do the analysis and then send you the particle size analysis result back. So even that is possible, but it would require integration. So the people don't have to do analysis themselves. They can send the image, take the image and say, well, this is the wheat flour, I'm looking what the particle size distribution is. Send that image, take the image, because quality of image is pretty good nowadays with the handheld devices. Send that to the lab, a central place, which can then do the analysis and say, this is the particle size distribution on this image.
One more question is, if I do, for example, 100 analysis for something on scanning electron microscope, I have the data.
Yeah.
Then I want to link it to something else, can I do it?
Like when you say,
analysis.
Again, depending on what you want to link it to.
That image on the camera, but sometimes I need to have a image of scanning electron microscope.
Yeah, so
the camera may not be as sophisticated.
No, it won't be. It can never be.
Yes, that's why.
So for example, if you have the scanning electron microscope images and then also have the digital images or images using the visible spectrum, and if you could show the correlation that this kind of distribution for the particles would give this kind of results in the scanning electron microscope, then you can show that correlation, and based on that you can then prediction on the new images that this is what this type of wheat flour is. So if
because we need to develop some less expensive the equipment every time you go for scanning electron microscope.
Yeah.
So if we can link it to the scanning, because minutely we can see the structure.
Yeah.
Then if we try to link with the image analysis,
I certainly would say it's possible, but like somebody would have to do that research or that analysis. So that you have the same sample is analyzed by optical imaging or imaging in visible spectrum, because the reason I'm emphasizing visible spectrum is because all the handheld nowadays handheld devices have the digital camera built in. So that would give you the visible image. And if you can take that visible image and then correlate with the scanning electron microscope or any other physical properties, then you can provide that result back based on that image. So that somebody has to do that correlation part of the research. Yeah.
So I don't know about the correlation of these two kinds of images, but we were working on some microscopic images and about the size of particles, especially fungal spores and others. So like Professor Nanak was saying, it is possible. There are some commercial softwares available, like one is imaging. It is freely available, and the particle size can be calculated very easily in your own computer, very easily using microscopic images. Imaging software is freely available. So all these things we can do
very fine level, 10 micrometer or less than 10
No
micrometer.
problem, sir. It can be.
We have to calibrate the...
Yeah, just you have to do the
If we have
calibration, yeah.
Some images, scanning electron microscope images, we can use those microscope images in that software.
No, for that we can do the calculation. I am saying because sometimes you don't have the scanning electron microscope. Then if we can have the image analysis capture and we can have a very minute level, is it possible to do that?
Like what I am understanding is you are having some images not from electron, maybe from a simple compound microscope. You can analyze those images also. But for the size, you have to standardize the size part using classical method of ocular and stage micrometer. And using that calibration in that software, you can do it very easily.
Yeah. I think basically what it requires is the calibration. And that's what somebody has to do, is the calibration. And you can do that calibration between different images. So whether it is a microscopic image, electron microscope image, or digital image you would take from the camera. And you just have to develop that correlation. And then so when you get next time image from a digital camera, you say this is equivalent to this because of the calibration. So that certainly is doable. But you need the images by 3 systems of the same sample to do develop that correlation. Yeah. Okay. Anything else? Okay. There are a couple more slides left. So we were talking about the fresh produce food products. So you can do the color texture evaluation of ready-to-eat meals, for example, quality grading of various meat based on color texture and estimation of fat content. So this is the meat grading you can do using visual images. Inspection of food packaging bottles for fill level and cap closure. And then you can use, once you have collected all this information, and this is on day 5th when we will talk about a lot more examples. This is just the simple arrangement which is showing of you is the process which could be where the image processing could be used for removal of the foreign objects or misshapen objects or defective objects. So in this particular case, your production process continues, and then here you could use, for example, a heating cooling unit, which may not be required depending on the application. If you're using thermal camera, you would need that, but if you are using just the visual camera, you probably won't need that. And then you would extract the features from the objects. So you take the camera, take the image, and based on the features, you could say this particular object belongs to this category. Then it will stay on the belt. If it doesn't belong, using either air jet or a drop device, there are many different mechanical ways you can then remove the defective object or the misshapen object or any foreign bodies from the processing line. So that's how you would integrate the image processing, and we will talk about a lot more examples on day 5 when we are discussing the applications in the automation of the food processing industry. The challenges to be overcome in applying image processing and sensors from not only from scientific point of view but also from societal point of view is especially from the image processing point of view. So like for example, if you had 2 wheat kernels together and you take the image and you then separate the image, so you can separate the background from the image, but 2 objects together, 2 wheat kernels together, the system would not know that there are 2 wheat kernels together. It would see that as a foreign object, okay, because it would not look like a wheat kernel. So something has to be done about that. So either you physically separate them, so you design mechanical systems to physically separate the objects. So objects are presented like separated kernels, or then you would have developed software or algorithm to separate those kernels before you do the analysis on them. So presentation of simulated object is still a challenge, and this is a challenge for engineers, particularly all the ag engineers. A lot of undergraduate theses can be done. That how you, so when you present dump the bulk sample and then ask move it separately, and then how it gives you the individual kernels on the surface, for example, is still a lot of work need to be done. selection of the significant wavelengths. So when you are collecting the information in a large wavelength range, you might identify that there is a 1 or 2 wavelengths where there is a much more separation in the features. And then you, by simply having those filters, you can collect the images very quickly, because like the more images you collect, more wavelength range you have, you are collecting a lot more data, and then analysis becomes a lot more complex. But if there are only 1 or 2 wavelengths of significance, you collect images only on those 2 wavelengths, and it's much easier to analyze the data. A speedy analysis of the spectral data is still a challenge, and we will talk about that when we talk about hyperspectral imaging or multispectral imaging. Integration of multiple image devices. So what that is still the problem need to be solved or need to be worked on. So for example, your digital camera or the visual camera might be able to look at the color, the surface characteristics or the shape characteristics, but then you need another camera, could be for example, X-ray camera next to it, which is looking at the internal defects in the object. Or you might be using a hyperspectral camera, and how you integrate these in the process line to be able to make the decisions using different spectral systems or different camera system. That work still needs to be done. Integration of multiple sensor outputs. So if you are, in addition to the imaging system, if you are using other sensors to collect the information, how you take that into consideration. So that integration needs to be done. And then industry still is reluctant to do a lot of automation. So adoption by industry need to happen. And the comfort of the retailers as consumers with technology, particularly with the nanotechnology, when you are trying to integrate that in the food products, and when there's a possibility of leaching of the nano compounds into the food material and consumer acceptance is not there. Similarly, when you say this has been inspected very carefully using the imaging systems and cameras, and consumers still are reluctant to say that is it as good as the human being did the inspection. So the comfort level of the consumers have to increase, and acceptability has to increase. And then retailers also has to feel comfortable that the system put in place guarantees you that safe, trusted food we are promising you. And then we need to reduce the false misclassifications, because that can give the wrong impression of the accuracy of the system. So when we are doing testing, we need to reduce those. Okay, so that's what I plan to cover today. I think we are probably about 3 hours. That's what I was planning to cover today. So are there any questions at this time? And then and if there are no questions, we have no tutorial today. But tomorrow, I think we should start at 10. And so I'm hoping then our lecture part would be done by 1 o'clock, so 10 to 1. Then we will have a lunch break. And then after lunch break, we would have a couple hour tutorials where we can do some exercises, and then start playing with the extraction of the features. And then if we can get MATLAB, then create some fake images, and then do some separation of the images, and then do some hands-on experience. If that doesn't work, we would do by hand, separation by hand, and you would see what effect it can have on the segmentation, and what effect segmentation could have on the size of the objects and the features of the object. Okay? Yeah.
Thank you very much for very nice presentation. What I want to, ask about the image analysis. For example, I have semolina. You understand semolina? I put semolina in a patty dish, I spread the particles, and I get the image of that. Now I want to develop a method which will tell what is the proportion of fine particle, maybe 0 to 10, what is the proportion of that, 10 to 20 micron, 20 to 30, 42. I just want to capture the image, and that program must tell immediately what is the proportion of fine particles, coarse particles, or medium coarse particles, number one. Second is, for example, I have a bread. I want to capture the image of the slice, and I want to say what is the uniformity in the particle size, whether the the grain size, we call it grain, or grain size is uniform, and what is the thickness of the cell? Is it thin or thick by image analysis? You understand? Third application could be very good in industry. For example, we have kidney bean, for example. You know, when we do the soaking of the kidney bean, after 24 hours, we have some hard-shelled grains. They never swell, right? But there is definitely difference in the size in the native grains, right? But because naked eye, it is very difficult to differentiate whether these grain will swell or not swell. But industry is facing a large or a great problem. How to identify, like for example, chickpea. Sometimes we have 30% harder to cook grain, but it is very difficult to identify this variety will have more or less, because it is just a wastage. Because when they do soak, they have to remove it. After that, they do the canning. Particularly for canning of chickpea, you can say canning of kidney bean, right? Third is that you have given a very good application, for example, color. It's a great issue in front of rice milling industry. That when we capture the color, particularly for parboiled rice, it should be golden yellow in color, right? So they have hunter color, the equipment, hunter color visible spectrophotometer. They capture, then they see what is the L value, what is A value, what is B value, and sometimes they don't get. But you know, we want to say this is the image, and this is the specification of our exporter, and we want to match. Okay, parboiling is good. This is the optimization. Third application I was talking in the morning, like we have, you know, for example, paddy. Paddy has hull. Hull texture varies from one variety to another variety, right? The surface texture. And the diffusion of water during parboiling process varies a lot. Of course, it is dependent upon temperature, but it varies with the time. For example, some variety, gets saturated in 24 hours, another 48 hours. And 48 hours or 24 hours is a lot of difference. And rice processor is facing a lot of problem. Now, can we see, okay, this type of texture or this type of varieties, they are not good. We should not go for parboiling, or we can give the direction to the plant breeder. Don't develop such varieties which have this type of texture, because they are getting more. Why? Because of this type of, the image or texture. We have to decide about that. Now the question is application. We have in front of us a lot of application, thousands of application, new application I can tell. But how to develop a system for that? Like what type of camera is required, how to get the camera, how to use MATLAB, how to extract, how to segment, like you are telling today, very good. For example, I just give you one more, the idea. In case of rice, right, we have actually, I tried 20 years ago, but I was unsuccessful. Maybe you people can work on that. Like when we do the milling of rice grain, here is the germ portion, right? So what I tried is, I tried to hypothetically doing like this to measure it. In some variety, the germ portion is bigger. In some variety, the germ portion is smaller. But it is not possible by measuring using some microscope, but image analysis can do it. Because to identify variety of rice is very easy if we can say that, okay, if this is the size of the germ portion, this belongs to this variety. Rather than going for thickness, okay, we can have the thickness, length, at different places we can measure the width net plus germ. Then we can develop a system. Okay, this system can be, okay, this is because basmati varieties are adulterated or they are, mixed with the low-cost varieties. Size is same, but the flavor or other things. So we need some system to find out which variety is there just by capturing the image. Because the plant breeder, they are unable to do it.
So I think what I would say, the examples you are giving, all of those examples, in my view, can be done by image processing. The work is needed is somebody to take on those as a research project and then develop the calibration database, the samples. Algorithm development nowadays is very, is not as cumbersome, especially if you use things like MATLAB. But even if you start writing your own program, the program itself doesn't take very long to develop the program or writing of the program. And some of it, as I say, we would do tomorrow. And you would see, if you have an inclination for writing the computer code, it's easy to write the program. And I think our team has developed a program which extracts 236 different features from the grain kernels, for example. But you don't have to write the program. You can use the existing codes. It's somebody taking the initiative to develop that correlation and that calibration, because that's what is needed for any of these applications. So,
for example, I have about 500 the accessions of kidney bean, 500, varying color, shape and everything, because I was having a DBT project for kidney bean, field pea. Now we have a lot of rice varieties, lot of wheat varieties, about 300 wheat varieties I have. So we can just think of how to classify that.
Well, that's certainly, to me, I think it's doable. It's one of the young profs here have to take the challenge, submit a grant to extramural funding agencies or intramural funding agencies, and submit projects. What this course, I'm hoping, would give you the tools that you feel comfortable in applying, and once you get the grant, that you can work on that project and then start solving the problems. Yeah. Okay.
Thank you.
All right.
Thank you very much. Tomorrow at 10 o'clock?
10 o'clock, yeah. So 10 to 1 we would have the lecture, then lunch, and then we will plan 2-hour tutorial.
Tomorrow I will arrange that well also.
Yeah.
I think I have arrived that it is.
Check it out.
It's here, it's in here.
Some of them, this one is